So hello everyone. So in this class we are going to learn about the grammars, which are context-free grammars, and we are going to learn the derivations that we can perform from the rules of the context-free grammars. So even before we go into the derivation process, we have to remember the definition of the context-free grammars and what is allowed on the right hand side and what is allowed on the left hand side. So four things make up the context-free grammars, and the V is nothing but the set of all the non-terminals, and we also call this as the rule alphabet. Sigma is nothing but the alphabet. What the string W is made up of is nothing but all the symbols or the combinations of the symbols which is picked up from the sigma. R is the set of rules that we are going to apply recursively in order to derive a string. Any string is set of all the terminals. And then S is the start symbol. So S is the start symbol, says that it is the first symbol in the rule of the grammar. Okay. So this is a revisit of just what is there in the definition of a context-free grammars. Unlike the regular grammars that we have seen in the previous module, the context-free grammars are more flexible compared to the regular grammars. So in the regular grammars, only three things were allowed on the right hand side, which was an epsilon. The second thing is a single terminal, and the third thing is the terminal followed by a single non-terminal. So apart from these three things, nothing was allowed on the right hand side. The left hand side of a regular grammar would always be a non-terminal. But then when we take up a contrast of it, which is a context-free grammar, then a context-free grammar will always have a non-terminal, that is a capital letter, on the left hand side. On the right hand side, the context-free grammars might have an epsilon, or it might have variables and terminals in any kind of order or combination. So this is much more flexible than the regular grammar, which allows only three things on the right hand side. So this is the gist of what is a context-free grammar. Okay. So in this class we are going to deal with the context-free languages. So when we call the context-free languages and grammars, so grammars will always lead into strings that belong to a language, and that language which is generated by the context-free grammar is called as the context-free language. Okay. So then we are going to deal with the derivations. Okay. So this derivation is a process of deriving some string S. Okay. I'll call this as small s from, say, capital S. So capital S, we know from the definition that it is the start symbol, and the small s is nothing but the set of all the terminals that make up a string that belong to this language. Okay. So this is what we are trying to do. So for this derivation from the capital S to the small s, we are supposed to apply rules of the grammar. So when we apply the rules of the grammar recursively, okay, they may be in any order, or they may be in any sequence, or it may be any number of times. So repetition of the rules is also possible. Okay. So once we do that, we will arrive at S. We are going to stop applying the rules when we arrive at the required string, which is S. Okay. And the entire system is called as the rewrite system. Rewrite system. So we call this as the rewrite system because only when we rewrite the rules and whatever is there on the right hand side of the rules, only then we are going to arrive at this S. So therefore it is called as the rewrite system. So we will see a simple algorithm which is given for the derivation, and that is simple rewrite. So what are we going to give to the rewrite system? So we are going to give R. So R is nothing but the set of rules, and W is the initial string. So what we do initially, so set the working string to W. So there is some W which is a working string, that is the initial string that we begin with, whatever is there in the rule of the start symbol. Until told by R to halt, we have to do two things. So first is match and the second one is replace. So we are going to do two things. One is a match, and after matching we are going to do a replace. So match what? The LHS of some rule against some part of the working string. So we are going to check the part of the working string and we are going to see which variable has got that part. Okay, so that is what we are matching. So once we find that, we know what is to be rewritten by what. Okay, so next is replacing. What do we replace? Whatever we have found, whatever matched part we have found from the rule of the grammar, that we are going to replace in that working string. Okay, so then at last we will reach some S, the desired S, that is nothing but the string, and we have to return the working string. So the working string which we initially placed is going to change now. Okay, so this is after all the replacements, we have to return the working string. So once we have seen what is the procedure for doing the derivation, we will see what are the types of derivations which are already existing. Okay, so there are two types of derivation. So any derivation can be classified into two things. Okay, so the first one is the LMD and RMD. So whenever you find LMD, so this is supposed to be leftmost derivation, leftmost derivation, and RMD stands for the rightmost derivation. So there are two types of derivation. The first one is the leftmost derivation and the second one is the rightmost derivation. So what is the difference between these two and why the different names are given for these derivations? In every step of the replacement, that is nothing but the step of 2.1, if we are replacing the leftmost variable in every step, then it is called as the leftmost derivation. In case we are replacing the rightmost variable in every step of derivation, then that kind of a derivation that we are doing is called as the rightmost derivation. So now we are going to look at an example. Okay, so for example, I will say generate the strings that belong to the language L is equal to a to the power of n, b to the power of n, where n is greater than or equal to 0. This is a constraint which is put on n is greater than or equal to 0. We have to understand that n can be equal to 0. That means even the string epsilon should be accepted by the grammar. So that means epsilon has to be generated by the rules of the grammar. So we'll write a simple rule of the grammar. So we say s goes to epsilon. This is necessary because in the starting itself it should accept some epsilon. Okay, next we say a is b. So by doing this, we are making sure that there is one a and there is to be a matching b. So if there is a single a, there has to be a single b. So in between this a and b, there could be one more a. So for every a which is generated, one b has to be generated. If another a is generated, a b has to be generated. So this part we will treat it as the variable s. Why we treat it as the variable s? Because the same s is going to generate one a that matches with one b. So therefore we have put this s in between, which can generate more number of a's and b's. So the number of a's and the number of b's is always equal, and that is preserved by this s. Okay, so now we are interested not in the grammar rule, but now we are interested in deriving a string. So let's take up some working string which is w, and we'll say I want 3 a's followed by 3 B's. 3 A's followed by 3 B's. So let's try to do the derivation for the same, and we'll see what kind of a derivation it is. Okay. So first thing, I have to select some production rule, okay, by matching whatever I want in the string. So epsilon, s goes to epsilon is just like terminating the entire derivation. So it's not possible for me to generate 3 A's and 3 B's with this production rule. So therefore we'll go with this production rule, s goes to A, S, B. So s goes to A, S and B. So we'll see what is the next symbol that I want to have in the string that I am going to generate. So this A is the second symbol. So we'll see which is the production that is generating the symbol A. So this is the production which is generating the symbol A. So therefore we may write here A. This S is replaced by ASB again, and this B is written as it is. We have just substituted for capital S. Then again this S has to be replaced. So therefore A and A, we are writing it as it is. So this A is what I have written here, and this A. So S has to be written here, rewritten, and this B and this B, we are going to write it as it is. So you need not write all these lines in between. This is only for the explanation purpose, to make you understand what we are trying to do and what we are actually doing. So S is replaced again by ASB. So we are using this production. Okay. So now you can see that whatever we require, that is 3 A's and 3 B's, is already there in the derivation. So therefore this S has to be removed from the entire list. So how to do that? We have another production that says S goes to epsilon. So we are going to use that production here and substitute it for epsilon. So epsilon concatenated with any string is not going to result in any changes in the string, because it is the identity of concatenation. So therefore 3 A's and 3 B's. Right. So we have done the derivation. But what do we observe here? So can I call this as the leftmost derivation, or can I call this as the rightmost derivation? So if you observe, in every step there is a single variable. So this is just the derivation. You can either call it as the rightmost derivation or call it as the leftmost derivation. In case if I am calling this as the leftmost derivation, so I am going to write LM on each step of the derivation. So S in every step and LM on the derivation. So since the same S is both the leftmost variable and the rightmost variable, I may even call this as a rightmost derivation. So every step I am going to write it as RM. Okay. So this is how we derive a string which is W by using the production rules of the grammar. Associated with the derivation, there is one more concept that we have to learn, and that is called as a parse tree. Any tree that we consider will have some root, will have some vertex or leaf node. So you must have seen the binary trees in your studies from the data structures. So therefore you have an idea of what is a tree and how it is represented. So therefore every tree will have some root, will have some vertex, will have some leaf node, which is the terminal nodes, which are called as leaf nodes. And what will happen if you encounter any production rule such as some A goes to x1, x2, x3 up to xn. So first of all, when we are dealing with the parse tree of a derivation, the root is always going to be the start symbol. And this start symbol in our grammar is represented as S. Then we have vertex. So vertex is a combination of three things. So the vertex can either be an epsilon, or it can be V, which is the set of all the non-terminals. That means all the capital letters which are found in the grammar, or it could just be the terminal symbols which are found on the sigma. Okay, so it could be the combination of epsilon, vertex and the symbols which are there from sigma. Again, we don't have any rule for the context free grammars, they are more flexible as I told before. So these things can be in any order or any sequence or in any number also. Leaf nodes. So the leaf nodes are usually the symbols from sigma, and these are nothing but the terminals, we call them. And what happens if you have any rule of the form where A goes to x1, x2, x3 up to xn, how to represent this as a tree? Then A will be the vertex, x1, x2, x3 up to some xn, there could be anything on the RHS. All of them are going to become the children of x. They are going to be the children of A. So the tree looks like A and the children are x1, x2, x3 up to some xn. Now that we know what is a grammar, what is a derivation, the types of derivation, that is the leftmost derivation and the rightmost derivation. We also know what is a parse tree which is associated with the derivation, and now we are going to learn one more concept, that is nothing but what is the yield of a tree. So yield of a tree is nothing but what produce the tree is going to give. So the yield of the tree is considered to be the string which is obtained by reading the leaf nodes from the left to the right, and we do not consider reading the epsilon symbols in the tree leaf nodes. So here, so the yield of a tree should result. Here the yield of the tree is nothing but something that results in the string that we are trying to derive from applying the rules of the grammar. Okay. So also let us now understand the difference between the leftmost derivation and the rightmost derivation by looking into the grammar which is given here. And we are supposed to derive a string from the grammar which is nothing but id plus id into id. So when you look at the grammar here, this is the grammar which is actually going to generate the expressions. Okay. So we can see that we have several operators here. We have plus, minus, star, divided by, power, and then id. id is nothing but something that replaces with numbers, or it could also be some variables when you consider the programming languages. Okay. So we'll start the derivation now. So first we will do the leftmost derivation, and next we are going to do the rightmost derivation. So every time when we are doing the derivation, we have to keep in mind what we are looking for. That means what kind of string we are looking for, what is the exact string that we are looking for. Now the leftmost derivation, so you can see that we have the plus operator and then we have the multiplication operator. So first we need id plus id. So since plus is there and multiplication is there, so only this production could be used and then this production could be used, correct? So all these productions are useless to us because the string that we are looking for, they don't have those operators at all. So that is how you have to decide upon what you are going to do. Apart from that, we see that IDs are there. So therefore this production is also definitely going to be used in the derivation. So let's start the derivation now. So E goes to E plus E, and here the derivation step is LM. So LM is nothing but the leftmost derivation. Within the brackets, you are also going to write the rule that we have used. What is the rule that we have used? The rule we have used is E goes to E plus E. This is the rule that we have used in the derivation step. We'll do the second step now. So E, since we are doing the leftmost derivation, we have to check which is the leftmost variable. So this is the leftmost variable. So this has to be replaced. So plus is there. So before this plus, what do we need? So plus is there. before this plus, what do we need? We need id in place of that e. So therefore, we are going to write here id, and we are going to use the production e goes to id. So this e is getting replaced by id. So therefore, id plus e is what we are going to write. Okay. So next step, again we are going to see which is the leftmost variable. So leftmost variable is this variable. So this is a terminal and this is a variable. So this becomes the leftmost variable. So e we are going to pick up, and we are going to see after id and plus. So after this part id and plus, what do we require after this? We need id star id. So there is no production that directly says id star id. Therefore, we have to use some production that has got the symbol multiplication, and that production is nothing but e goes to e star and e. So this is the production from which we may derive at later steps id star id. So therefore, we are going to use this. So what do we write here? id remains as it is. So in place of this e, we are going to write e star e. So write here e star e. Next also step is to determine which is the next leftmost variable. So this is the next leftmost variable. So therefore, e goes to id. But what do we require here in this place after this plus? So after this plus, id is required. So therefore, this e has to be replaced by id. So which is the production that I am going to use? E goes to id production. So therefore, we write here e goes to id and write here id star e. So this e we haven't replaced yet. Next, in this entire production rule, find out which is the leftmost variable. So this is the leftmost variable. So after this id star, in this place we require a id. Therefore, again I am going to use the production e goes to id and replace in the entire production rule star id. So this is how we do the derivation. So we stop at this point because we have arrived at what string we wanted. So we are going to stop the derivation at this step. Okay. So once we have done this, we'll write the tree for this. So tree starts from the first step of the derivation. So e plus e. So this acts as a1, a2, a3, or rather I had written a goes to x1, x2, x3. So e has got 3 children. What are they? Whatever is there on the LHS, rather whatever is there on the RHS. Okay. So e plus e. Okay. Then this e is replaced by id. So write id here. Its child is id. Then this e is replaced with e star e. This id is replaced by e star e. So this e has got 3 things. What are they? E star e. Next, this e is replaced by id. So this e is actually getting replaced by id. Next, this e is getting replaced by id. So this e has got replaced by id. Now we'll see what is the yield of the tree, and this is nothing but your parse tree. This is parse tree. So we'll see what is the yield. So how to determine the yield? Yield is nothing but the set of all the terminals which are read from left to right. So this is a terminal, next this is a terminal, then this is the terminal, this is the terminal, this is the terminal. So this is the yield of the tree. We'll go on reading them one by one from left to right. What do we get? First thing I get on the leftmost position is id. After that I have plus, then I have id. After that comes the star, and then after that you have id. So this is the yield of the tree. So in this we have seen what is a leftmost derivation, and we have done the derivation and we have produced the or written the parse tree for the same, and we have also determined what is the yield of this tree. So on the same lines, now we will keep the same grammar, we will keep the same string that we have to derive, but this time we will see how to perform the rightmost derivation. So we'll write here RMD. So every time we have to make sure that the rightmost variable is the one which is getting replaced in every step. Okay, so in the rightmost derivation, we will start with E goes to E plus E. So E plus E is anywhere required, we write that. Next we have to see which is the rightmost variable. So this is the rightmost variable. So do you see the difference? Here we have replaced this E first because this was the leftmost, and here we are replacing this E because this is the rightmost variable. So this E has to be replaced. So we have to check what do we require after plus. So after plus, ID star ID is required. First time I have used E plus E. So second time when we do the derivation, so this E has to be replaced with E star E. So plus E star E, that is what we write. Next we are going to determine which is the rightmost. So this is the rightmost, and what we require in that place? We require a ID in that place. So therefore E goes to ID. E goes to ID. So if it is E goes to ID, then E plus E star ID. This is what we are going to get in the derivation. So next step, we have to replace the next rightmost variable. So next rightmost variable is this E. So therefore this E again has to be replaced by ID. By now you would have had an idea why I am replacing that E by ID, because in that place of that variable I require ID. So therefore E goes to ID is what we are going to use. So then it is E goes to ID. So therefore E plus ID star ID. This is what will happen if I replace E by ID. Next we have E goes to ID again. Why? Because in this place also we require ID. So E goes to ID plus ID star ID. So do we stop the derivation here? So yes, we stop the derivation here because we have already got what string we were intended to derive. Okay, so we have stopped the derivation here. So we'll write the derivation tree for the same. So we'll write the derivation tree. See, I am using the term derivation tree, and sometimes we call it as a parse tree also. So both are one and the same. The parse tree and the derivation tree mean the same thing. So we'll write the derivation tree here. So first thing, we have started with E, and E goes to E plus E. So E plus E are the children of this E. So E plus E. Next, E goes to E star E. So we have to look into which E is actually getting replaced. So this last E is getting replaced. So this part of it is getting replaced by again three things. What is that? E star E. So this is what we do. Next we are going to check which is the element which is getting replaced. So this middle, rather this E is getting replaced. So this E, last E is getting replaced by ID. Next, middle, this E, second E is getting replaced by ID in the next step. So this E goes to ID. Then next we have this E which is getting replaced by ID. In the tree it is this E which is getting replaced by ID. So this is the complete parse tree that we have obtained. And we will see what is the yield of the tree. So yield of the tree is nothing but every terminal which is read from left to right. So we will go on reading all the terminal, that is the leaf nodes from left to right. So ID is the first thing that we read. From here we read plus, from here we read ID, from here we read star, and from here we read ID. So therefore it is the same W that we have derived from the derivation, and also the yield of the tree is the same string. So this is the difference between the derivations, the two types of derivations. So, first one is called as the leftmost derivation, where in every step of the derivation the leftmost variable is first identified and that variable is replaced with what has to match the string that we are trying to derive. In the second type, that is the rightmost derivation, we are looking for the rightmost variable and we replace the rightmost variable at every step. Okay. So, this is the two types of derivations that we are going to do. Like we wrote LM on the derivation steps of the leftmost derivation, we are going to write RM on the derivation step of the rightmost derivation. So, this is to tell anybody who is reading into the derivation as to what kind of derivations have been made. So, if we want to wrap up the class, we will discuss what we have discussed today. We have revisited the definition of a grammar and then we understood what is derivation. So, in order to do the derivation, we just wrote some steps which is also called as the rewrite step, and we saw 3 steps in that rewrite algorithm. Then we understood what is a derivation and how to apply the rules of the grammar in order to derive a string. So, there could be a single variable and the same variable could be the leftmost variable also and the rightmost variable also. So, we can't do any distinctions about whether it is a leftmost derivation or the rightmost derivation. But whenever possible, like in this example, we can replace the leftmost variable every time or we can replace the rightmost variable every time. So, then we have to determine or we have to differentiate them as leftmost derivation and rightmost derivation. And we studied what is a parse tree and what will be there in the root of the parse tree, what are the vertex of the parse tree and what is the leaf nodes of the parse tree. So, for any derivation we can represent it with the parse tree, and once we have designed the parse tree we can frame the yield of the parse tree. So, this is about the different types of derivations that exist for any grammar rules. Thank you.